Hello, everyone, and welcome to today's presentation on structural health monitoring. My name is Ryan Lovely, and I am a project manager at mageba North America, and I'll be your host today. Also, a warm welcome to Daniel Beatley and Andrea Patriaconi, engineers at mageba. I'm pleased to introduce them as today's speakers, and they'll help guide us through this presentation. Daniel is a ABET mechanical engineer, specialist at mageba with bridge bearings, including RoboSmart for bearings, and he has more than 10 years of engineering experience. Andrea is a Master in Science of Engineering, specialist in structural health monitoring, and he has more than 5 years of experience. Before I hand over the mic, I have a few housekeeping items to address about the presentation and the webinar platform. Firstly, for those of you seeking PDH credits, this course will offer 1 continuing education credit, and you'll receive the course certificate via email after the presentation. This course is registered with the Practicing Institute of Engineers, course number 202-07310. Next, we'd love to hear from you during today's presentation. If you have any questions for the speaker, please feel free to type in the chat box. Just hit the downward arrow and you can open it up and send us a message, and we'll address it towards the end of the presentation. Also, during the presentation, we'll be submitting a handout to you that you can reference at any time if you'd like to take a look at any of the slides from the presentation. So, without further ado, I'd like to kick things off by welcoming our first speaker, Daniel, who will be telling us a lot of interesting information about the structural health monitoring system. And now over to you, Daniel. Thanks.
Great, and thanks, Ryan, for the introduction. So let's get started with the presentation. So just as a look at what we'll be talking about, we'll start with an overview of the status of America's infrastructure. We'll move on to an introduction of exactly what structural health monitoring is. We'll look at some reference projects, at which point I'll bid you adieu, and Andrea will take over and give you some nice detailed looks at the added value of structural health monitoring. We'll draw some conclusions, and then we'll do a little question and answer after that. So let's get started with the overview of America's infrastructure. So for some context here, every 4 years, the American Society of Civil Engineers puts out a report card. In 2017, specifically in the bridge category, we can see there that the rating or the grade was a C+. The basis of that grade is the physical condition and the necessary investments in that particular category of infrastructure. So that would indicate that there is clearly some work and investment required. But the question is, where exactly is that work required? And for that, we get into some stats, but without just dryly reading the numbers, we can kind of summarize it by saying that there are hundreds of thousands of old bridges, say 50 years or older. Tens of thousands of those are structurally deficient. And of course, the bridges are not getting any younger, approaching the end of their design life. And the rehabilitation backlog of 123 billion gives us a place to start. And by understanding these structures better using structural health monitoring, we can prioritize the requisite work to the most critical parts of the structure and thereby really allocate funds efficiently. So that is the objective. And to sort of further support the idea, we can look at the National Academy of Engineering. They list among their grand challenges currently the restoration and improvement of urban infrastructure. So again, structural health monitoring really fits this objective, and we'll see exactly how. And yep, for that we introduce structural health monitoring itself. And the question, I guess, that we seek to answer, and especially with this introduction slide, is how exactly does structural health monitoring help to meet the grand challenges spoken about on the previous slide and by the National Academy of Engineering? And we put it into 4 kind of large categories. Of course, safety being right at the top. those sort of concerns like structural capacity, stability, ultimate capacity, generally speaking, just the safety of the structure. That's what monitoring will lend itself towards. Things like fatigue as a specific example, and we'll see how as we go forward. Then during the service life of the structure, we want to get design versus real data, which structural health monitoring is crucial in. And then of course the optimization of maintenance work as the structure ages. During construction phases, we'll have an example of that going forward, but taking measurements and getting important data through the stages of construction can be really crucial. And then of course, as a specific example of that, something like the forces present in cables, and we'll take several looks at exactly how that works. Then during the end of service life of a structure, which really speaks directly to those challenges earlier, we want to prolong that life as much as possible, and that has an obvious cost benefit, of course. And then to assess and prioritize the refurbishment work that would be necessary on the structure. Basically, we look to gain the benefit of a better understanding of the real behavior of the structure. In terms of the key components, just a kind of a broad overview of what a structural health monitoring system looks like in the process flow. It would start on the right side, lower right side of the slide at the object, of course. So this is our bridge, our building, our dam, something of that nature. And then we want to measure certain values on that object, of course. From there, we select instruments and cabling for those instruments to measure the specific pieces. We then move through data collection, interrogation into the software that is used to process the data, finally to the end user, kicked back in his chair there, that could view the data then on an interface. And when the data comes out, the objective is to have some sort of easy to interpret, like this kind of makeshift graph there of a change in the behavior that could be indicative of something important. Categorically, there are two groups we'll talk about in some more detail, but those will be short-term, temporary, or portable systems, and then long-term, permanent, automated type of systems. In terms of the strict definition of a structural health monitoring system, we would say that it's an assembly of sophisticated electronic devices installed on civil structures with the purpose of measuring physical parameters and then consequently assessing the actual conditions of the structure. For a kind of a typical scheme of what those sensors may look like, we can take a little snapshot of the Wazirabad Bridge in Delhi, India. Of course, the cable stayed bridge, many different types of sensors you can see on the little upper right-hand key there. And like I mentioned before, if we want to kind of zoom in on a particular part, we look at the green squares, the accelerometers, and they're one of many sensors, but there are many of that particular sensor on this example. And in that case, we would seek to estimate the force using dominant cable frequency. And this is a measurement not easy to take any other way, really. And then just to kind of highlight another sensor, in this case a sensor suite, it would be a weather station right at the top of the tower there. And of course, weather is extremely useful for a lot of things on a bridge, but specifically for regression models, which we'll have a really specific look at near the end of my part of the presentation. But as you can see, lots of sensors, lots of uses for those sensors. In terms of what a typical automated, so there were those two categories, the short-term temporary system. This is the automated long-term type of structural health monitoring system. And here we start on the lower left of the slide, the bridge monitoring computer, sometimes called the master station. You could think of it as the brain of the nervous system of the structural health monitoring system, if you like. Basically, all the sensors and data acquisition units collect their data here in the bridge monitoring computer. This data is then transmitted. That's what the horizontal red line at the bottom is. In this example, it would be something like 3 or 4G wireless transmission to a server room, where the data is then filtered through the internet finally to a remote user that sees the data, much like in the previous example, at an interface, and we'll look at what that may look like. So this would be something like a typical login port of the user interface, of course, remotely accessed and within some personalized features. And so once you log in, you may be greeted with something like this, a dashboard, if you will. And what this is a system overview. These would be real-time values, and as you can see, quite a number of them. So a broad snapshot, but to narrow to some important components, alarm values, min, max values, things like that can be set so that really you log in and then have a nice overview of the current real-time behavior pretty quickly. And of course, this for a cable stayed type of bridge. In more pages of the user interface, maybe something like this. This is a clearly more detailed view, and what we're looking at is 1 week of data. And top to bottom, we have wind direction and speed, then the structural temperature at several locations on the structure, as well as the main span displacement also at several locations on the structure. Of course, the time window can be set. In the example here, we have a week, but this could be hours, months, lots of options there, of course, for graphical representation. And then the data is not merely inside the interface, but can be downloaded for analysis or reporting via other softwares. And then automated reports are also available, something like a monthly summary. So you do get those updates even not necessarily logging in. And so, you know, as I mentioned just a couple slides ago, there are 2 general categories of structural health monitoring systems. That's the short-term temporary portable type and the long-term permanent automated type. Starting at the top here, we have the short-term system, typically to get a specific sort of set of data about a particular thing. Andrea will actually show you a really great example of where this was extremely useful. And something like an intervention work would be a great example of use for the short-term systems. And then, of course, typically a smaller quantity of sensors, but yeah, sensors, the same sensors nonetheless, typically just fewer of them. For the long-term permanent automated type of system, this typically is a system installed over multiple years, designed to be used for quite some time. The sensor arrays can be cabled or wireless. We'll see an example of that as well. This, of course, is based on the application necessary. And sampling rate is also a part of the decision-making process, and of course, sensor type. These will have more sensors, as you can see, some 250 in a particular example, but upwards of there even. And then, of course, the web user interface would be a feature of the permanent system as well that we just took a look at. So the question of what exactly can be measured by a structural health monitoring system, the answer is a lot of things, but we're going to try to hit some highlights here. So starting in the upper left, we have the forces at bearings can be measured. Here, we're looking at a pressure sensor that's in the elastomer well of a pot bearing. And since bearings are wear items, this type of information is extremely crucial for you know, getting an idea of the lifespan of these particular pieces. Just as an example of, you know, how the sensor data may work, is this is a pressure sensor, and it's we can use the pressure inside a pot well because of the flexibility of the elastomer to get pretty accurate pressure data or pressure estimates, let's call them, but you know, something like plus minus 5% with a pot bearing. So we really know how that bearing is being affected in the real world, as opposed to simply calculative data. Upper right, we have displacement sensor there. This is the second of the 4 vital pieces for a bearing in particular. But the displacement sensor, as you'll see, can be used in many different locations. So we'll take closer look at those in a little bit as well. And like I mentioned, lower left, we have a weather station. Temperature is a crucial piece, of course. Humidity, wind speed and direction can factor into load factors, and those can be double checked. And then of course, things like rainfall, we know can become very crucial. The strain gauges, finally lower right. Stress and strain relationships are well understood for most materials, or for, let's say, many materials. This is a direct window into the behavior of the material. And this is a great example of how we can compare calculations to real world data with something like the strain on a steel piece of rebar. And as I mentioned before, as we saw in the Zero bod, we can take accelerometer data that we see on the upper left here, and that can be used to extrapolate cable forces. It can be used in other parts of the bridge, I promise, not just cables. We'll see an example of that as well. On the upper right, we have the ladder corrosion sensor, an interesting sensor because it's the only chemical attribute sensor on the list. It gives indicators for the onset of the rate and or rate of corrosion. It's embedded, as you can see there, at rebar depth, and it's deliberately positioned at that sort of angle. You can see it's above one set of rebar and below the other. It measures the potential, the resistivity, and the linear polarization resistance of the concrete, which gives, together with temperature, as you can see the temperature probe just below the corrosion sensor there. So when you combine the corrosion sensor, temperature, and humidity, it lends the ability to calculate rate of corrosion. Crack opening sensors on the lower left. It's a distance sensor, but a more accurate one with static mounts on either side of the slider you can see there. And then finally, of course, GPS. There's GPS in everything these days, and bridges are one of those things. And one of the latest developments and exciting developments because of the benefits that it yields is this LoRa wireless system. And as before, we have a pressure sensor in the bearing. This time it's a spherical bearing, but the concept is the same. That is wired to the node that we see there in the second part of the upper diagram chain. But from there on, it's completely wireless, and that is a lot fewer wires than what we saw before. But of course, same thing to the gateway, a collection of sensors, and then out to the antenna, the cloud, and finally the end user in a similar way as we saw before. And in terms of the benefits of this system, they are both straightforward and significant. For low frequency measurements, it's a perfect application. In terms of its reach, it's 9 miles over clear terrain, but even in city terrain, in the realm of 2 to 3 miles, which is certainly plenty to get from a bridge to a cell tower in most places. One benefit that's not clear from this little diagram at the top is that it uses long life batteries, so does not need mains power. And that's a pretty big deal, not just from being not dependent on mains power, but also because it dramatically reduces the amount of wiring required to set this sort of system up. And then obviously we're also taking out the cables between nodes and gateway, and so that's another big reduction of labor and materials, and then thereby wear. So significant reduction there. This of course accelerates the on-site work, and a system like this can take upwards of 500 sensors. So every specific example you'll see today falls into that category. So also a very broadly applicable system. And then of course, IP67 ratings and temperature ratings are non-trivial, so will work in a lot of environments. And if we can sum it up, we would say that it's robust, fast, and power saving. So after that introduction, I hope you kind of have a general concept of what SHM looks like, and now we'll take a specific look at some example projects. And these are all example projects, but we don't have time to look at all of them. We talked about there was Zero bod just now. We will go into detail about the new Champlain. We'll also take a look at the Incheon, and these are other projects, but those are the ones we'll get into specifically. And yep, off to the races with the new Champlain. It replaces the Champlain Bridge, which originally opened in 1962 in Montreal, Canada. The structure carries currently 160 vehicles per day across the St. Lawrence River. Structural health monitoring in this case will enable the optimization of performance, maintenance, and rehabilitation, and it will be done on an ongoing basis, so one of those permanent systems we talked about. And it's comprised of 250 sensors, and it's not a standalone system in Montreal. It is part of a state-of-the-art asset information monitoring system, which we'll take a closer look at as well, or at least an overview of what the concept is there in Montreal. This new bridge is 2.1 miles long. It includes a cable stage structure that you could see in that previous picture maybe, with a main span of 240 meters. The superstructure, as we see on the left side of this selection of drawings here, is designed as 3 independent parallel structures, so those structures you see at the top. The outside two are 3-lane vehicular traffic corridors, and the center is a rail transit corridor that has 2 lanes. And each structural health monitoring system element is carefully detailed as shown in this particular slide. And the way those details work is they start on the left with the structural overview, of course, then goes into detail of the structural component where the sensors will be mounted, which is the upper right little cluster of drawings, and then finally the detail of the sensor itself, including a wiring bundle and protective box there. In terms of the system architecture of the new Champlain Bridge, this is a graphical representation, but basically that entire bottom row, we can start from the bottom up, basically. The bottom row, that would all be sensors. Each little vertical line represents a single sensor. These gather in the data acquisition units, which is the second row, then through a technical network into the master station at the west abutment. The new Champlain Bridge has 22 such data acquisition units feeding into the west abutment facility. And then from there, data is transferred into the traffic management center. And this is where that AIMS system is that I was talking about. And as you can see on the bottom of the slide here, the AIMS is comprised not only of our structural health monitoring system, but an intelligent traffic system, a pavement management system, a traffic management system, and an environment management system. So lots of these systematic pieces there. And we are one of the group, and all of that is managed at the traffic management center there. In terms of the sensor installation itself, a large number of the sensors on the new Champlain have already been installed, and the top 2 pictures are good examples of the internal sensors. And we spoke about both of these, strain gauges on the left and corrosion sensors on the right. And these were really due to an acute awareness by the customer that they needed long-term durability. And these corrosion and strain sensors have been widely used at select locations. And just like we talked about before, they're used for early indication of corrosion, which can lead to degradation. That's a common understanding, is that corrosion is a thing. It's not easy to detect, and these are ways that we can do it. And then for the non-invasive type of sensors, or the external sensors, we can call them, the lower 2 pictures show a displacement draw wire sensor there at a joint location, and an accelerometer that's not on a stay cable on the lower right. So those are just examples of other sensors on the new Champlain. We can move forward to a landmark bridge in the US, the Delaware Memorial Bridge. It's a twin suspension bridge. It carries I-25 and US 40 across the Delaware River between Delaware and New Jersey. It was designed by HNTB with help from Othmar Aman, a Swiss engineer. The focus here is on 16 pin and link structures that connect the truss girder to the towers. You can see in this lower drawing, there's little clusters of red there. We'll zoom much further in, so you'll get a better look at those. But that's what the main focus of this project was on. And the important thing on the Delaware that we want to talk about is there are 2 phases of monitoring. The first phase is monitoring during construction to set some baselines, and then a permanent system of monitoring on some bearings. So a good example of two different phases. So the original pin and link structure on the left is to be replaced by modern spherical bearings on the right. The spherical bearings are going to be capable of all, of course, the required movements, loads, and rotations, as well as very frequent uplift, which is a big deal for bearings, and so it's a good example of where monitoring will be crucial. So, yep, still during the construction phase here, before the bearings are installed, it's necessary to establish a baseline of forces, movements, all the reactions at those locations. And so strain gauges, tilt meters, and displacement sensors will be used. And what we're looking at on this slide is some of the 80 strain gauges that are located on the truss diagonals, and they provide information on the load transfer between the girder and the end links. So we'll just do a quick sweep of the slide here. That's where the strain gauges are located. The upper left picture, that little blue set of arrows there, shows where the strain gauges are actually mounted on the girder, and then how they are mounted is the very next picture, and that's a great picture of a data acquisition unit. So in those diagrams before, we saw DAUs, data acquisition units, but that's actually what the physical object looks like, and it's where the strain gauges are collected. All the wiring groups at the bottom, those are the strain gauges, and then what the data would look like on the web interface is on the lower right. So each one of those lines represents a strain gauge, for example. In terms of the transverse and longitudinal sensors, this is what they look like, and they give us an understanding of the existing bridge movement. So remember, again, this is construction phase, setting baselines, getting existing data. On the upper left, we have a ultrasonic sensor between the deck and the tower. On the upper right, we have a diagram of a draw wire sensor between the truss girder ends and the tower. And then, of course, lower left, another draw wire sensor between fixed tower on the left and movable truss on the right. And then finally, a spot measuring temperature sensor there, which will be important. We'll see a regression model, but those are used at different points on the bridge to get temperature discrepancies. The Delaware Memorial web user interface was provided, and of course, all measured data points are in there, and a relatively unique thing about the Delaware Memorial, but in my opinion, a really useful piece, is that there are also images and drawings of the sensor setups. So when referencing the data points, it's clear exactly what sensor and where that's coming from. So that's a convenient piece that was added here. And of course, the data is available 24/7. So now on to the permanent phase. So again, construction phase was everything we just looked at. Now the bearings come in to replace those pin and link structures. And this is what we have, 16 spherical bearings in total, with as much as plus minus 23 inches of movement, which is a non-trivial amount. And for this particular situation, we want to have a constant understanding of the bearing performance. This particular slide here shows a draw wire sensor, the sensor itself on the lower left, the design of that sensor just above it, and then on the right side, an example of specific installations of those sensors, shots directly from the shop, so an actual installation of those there. And then same bearings, but this is a new or another type of sensor. It's not an and/or. These are in addition to the draw wire, and these are 2-axis tilt meters. Don't worry, the shot on the lower left there is of the inside of the sensor, but it is not open to the environment when it rides on the bearing. You can see on the right side the same tilt meter, but enclosed and sealed. These also have IP ratings, so that is the sensor setup you can see. And I mentioned earlier that there are 4 crucial parameters for a bearing, and because of their status as wear items, this becomes crucial. So the load on the bearing, we saw the pressure sensor that we could extrapolate the load on the bearing from there. movements and frequencies of movements we have from these draw wire type sensors, or even ultrasonic sensors in some cases. But here this example is draw wire. And then this 2-axis tilt meter gives us all of our relevant rotations. And then finally, and maybe the most cutting edge of the sensors is a inductive sensor for sliding surface wear. So what this gives us basically is the thickness of the remaining sliding material, which for bearings like this that's going to do a lot of moving, this will be another really crucial piece of data. So that gives us kind of our entire overview of a given bearing, those four pieces. So that's really defined bearings nicely, and we'll go into modular expansion joints a little bit. We'll take a bridge example and then move on from there. So the modular expansion joint is a collection of lamella beams. So on the top left picture here, going into the screen, we have the on top of the lamella beams. And what those do basically is divide a larger movement into a collection of small movements, which gives these joints their incredible capacity. The support bars beneath the lamella beams are attached and form a non-rigid collection of connections. It's a non-rigid connection, so its ability to move in a lot of different directions is the reason why monitoring on these joints is crucial. And the real important part about modular expansion joints is that they have such incredible longitudinal movements, more than any other type of joint, which is over 6.5 feet in some cases. In the example, we'll see it's about 6.3, but has significant distance of movement, and of course watertight. It's not easy to see, but there are little rubber seals between each lamella beam in the top diagram, and we can of course monitor movement and tilt on these type of joints. The specific example is the Incheon Grand in South Korea. It has a main span of 1.6 miles, and like I said, quite a large movement capacity of almost 6.5 feet. And in this particular case, we were very interested in these movements, particularly for fatigue considerations, and overall we came out with very satisfactory information. But we'll take a look at what the setup looks like. So it's a relatively small but extremely useful system. 4 ultrasonic sensors measure the smaller distances that you can see in the diagram at the bottom. Well, furthest bottom left, let's say, that would be an ultrasonic sensor location. And then the draw wire sensors for the longer distances, as we've seen before, but this little cylindrical sensor is the draw wire. And the most maybe crucial part of this group of pictures here is this RoboSmart Internet of Things master station. So we talked a lot about the brain and the master station behind these sensor systems, and that is what one looks like right there on the left upper left picture. So and yep, this group of sensors was able to really get some useful data. As you can see here, this is a 4 and a 5 year oscillating graph, or 4 year on the left, 5 year on the right, oscillating graphs. And I spoke a little bit about temperature regression, and this is a excellent example of why that's necessary, because these are not movements, positive and negatively. This is temperature effect. So summer and winter of each of these 4 and 5 years. And so it is crucial that this temperature gets regressed out, and that's what gives the nice flat line at the bottom, which could be used to detect unfavorable trends, let's call them. But without that, of course, without these temperature regressions, it would not be so clear. So just an indication of how the sensors kind of work in harmony together. So that is about all from me. Hopefully you got a good overview, an introduction, saw some reference projects, and now we're going to move on to some added value propositions from Andrea there. And just as a reminder, questions, post them there in the chat. And if for some reason that doesn't work, there'll be email. There's lots of ways to get in touch with us. So, but definitely give us all your questions. So, but yeah, without further ado, Andrea, over to you.
Thanks, Daniel. We can talk now in this last part of the presentation about the benefits and added values of a monitoring system on a bridge. And we want to do it presenting some key projects that mageba delivered in the last few years. The first example, this first example is a bridge in Bouriette, in the east part of Switzerland. Here, the added value is that the monitoring system controls the structural forces on the bridge and provides an automated warning to the owners and to the engineers in case something is not as expected. To explain to you a bit the context, some years ago, an important structural refurbishment was designed for this bridge because with the time it became a more important infrastructure, traffic loads had increased and also settlements were observed. Therefore, the engineers were concerned a bit about the structural capacity because of the increased loads and also because of the different load distribution due to the settlements. For example, in the picture on the bottom right, you can see also the new steel shear reinforcement applied to the longitudinal beams. For this project, we provided smart bearings with load sensors integrated to give to the engineers measurements of the real forces on the bearings on top of the piers. And it was very important to know these values because the loads in the bearings somehow correspond to the shear forces in the beams. No? So they know how close or far the bridge is from the safety margin that they used. In addition to this, with these measurements, they have an information also about settlements, because if it happens, for example, they could observe a different load distribution among the bearings. They could see an increasing trend if the settlement happens in the abutment, or a decreasing trend if it happens in the piers. So to conclude, with this monitoring system, we can see at any time if the structure is within the safety margin. And in case an automatic warning system sends an email to us and to the engineers anytime one of the reading crosses a predefined threshold. This is another good example of added values of a monitoring system, which in this case played an important role to extend the life of the existing structure thanks to more advanced measurements and analysis. This viaduct is an important highway built around the 70s near Bern in Switzerland. The structure is a multi-span pre-stressed box girder, and after 40 years of service, considerable cracks were observed in the girder soffit during an inspection, and these cracks were up to more or less mid-height of the box girder, close to the construction joint of the bridge segments. The engineers could not know exactly when and why this cracking had begun, but obviously concerns about the structural safety were raised. So more detailed studies started, and it seems it was a combination of factors like shrinkage, increased traffic loads, or also as a result of the staged concrete casting and pre-stressing process. The monitoring system for this project was provided to measure strains and cracks opening in 3 critical cross sections. So 3 construction joints, which are the section near the pier N O P that you see on the picture on the top. Here you see the concept and the installation. LVDT sensors were installed on the concrete surface to measure the cracks opening, and strain gauges were mounted on some of the rebars crossing the structural joint, so on the rebars crossing the cracks. These measurements were used to correlate the crack opening to the strain of the rebars, and then to evaluate the fatigue damaging stresses in the rebars. Sampling rate was 200 Hz, so 200 readings per second, because it was important to see the effects of the traffic loads. Here we see finally some of the results and the conclusions. On the left, there are 2 pictures from another project, a more recent project that we have done last year. And these are for illustrative purpose to show how the data looks like. The chart on top shows 5 days of data. We can see the thermal wave for the for the alternation of days and nights. We can see the amplitude of the cycles in megapascal and also a zoom of a single vehicle event. You can see how it looks like. On the bottom, we see the picture of a live event with passing vehicles. The chart in the top mid shows the linear relationship within the cracks opening and the strain of the rebar. This relationship, together with the Oakes law, was used to convert the measured cracks opening in stresses of the lower rebars. And finally, on the right, you can see an example of an histogram which summarizes fatigue analysis. It represents for each level of stress in megapascal in the horizontal axis, the number of cycles occurred. And these are the key parameters for fatigue analysis, amplitudes and number of cycles. This analysis showed basically that a very low level of fatigue damage was occurring in the rebars, and thanks to this, the owner saved a lot of money because the monitoring service costed approximately 150,000 euro, more or less 160,000 US dollars. But it proved that the problem was much smaller than expected. So no important refurbishment work was needed. They did not have to close the bridge or demolish it to build a new one. But they had to do only minor improvement works, and thanks to this, the owner probably saved something like a considerable amount. Here we see another example where the monitoring system was provided for two bridges, McDonald and Mackay Bridge in the city of Halifax in Canada. The goal here was to monitor the behavior of the joints to get realistic values of their performances in terms of opening and closing of the joint, and to observe the more extreme movements and rotations. The data were used to assess the accumulated movement and deduce sliding material requirements. Here we see some of the analysis, and not all the results were as expected. In the bottom left, there is the linear correlation between the joint opening and the temperature. This is also to confirm the design of the joint. In the two charts on the right, we see the accumulated movement for the two bridges. The one on top is McDonald, the one on the bottom is Mackay. And here we can see that the accumulated movement for the McDonald was much less than the one for Mackay. So a very different behavior was observed for the two joints, even though the structures and bridge lengths were pretty much similar. And this was important to find out that something was not performing as it was supposed to be. In this slide, we see the example of the new Kavaru Bridge in New Zealand. Here, the monitoring system was used to confirm the performances of the STU, shock transmission unit, after the structure completion. So, to validate the design assumptions by comparing the results. The bridge is a steel arch structure, and the STU were placed at both abutments. The designer wanted to know how these STU were performing. So a proper load test was organized, also for a real truck braking event. Sensors used were accelerometers on the structure and pressure sensors on the STU to measure the pressure in the chamber. Here we see some results in terms of acceleration of the bridge and pressure in the dampers, measurements that were used to confirm the real behavior and validate the design. One of the most important added values is that in general, a monitoring system makes automatic measurements that were previously manual. So with the need for someone to go physically on site, no matter what measurements are to be done, a monitoring system can operate 24/7, so can provide a comprehensive information to understand behaviors, trends, and performances over days, seasons, for different weather conditions or traffic scenarios. At the contrary, visual inspection provides a sparse information typical of a periodic visit, which is an isolated measurement that can say how things are in that specific timing point, but it does not give an overview of the performances and behavior. Also, the quality and accuracy of the information is much higher with a proper monitoring system rather than a visual inspection. For example, if we think about the crack opening, we achieve an accuracy in order of microstrains with the sensors. Also, there are other measurements that actually cannot even be done by the operator. For example, measurements for fatigue analysis. And this is true for every system, even for a simple portable system. A project with few sensors, it does not necessarily need to be a big, sophisticated or expensive system. Obviously, also visual inspection are still important to get an overview of what's going on site. But if more detailed information are needed, then a monitoring system becomes very important. Also, with a monitoring system, there are no limits in what can be done to address any possible request and special need of the client. A monitoring system provides useful and usable information and data to support studies and analysis for the engineers to understand how really things are and solve problems. Okay, it's not always easy, it's not always quick, but it can provide information that clarifies doubts and answers concerns that quite often could not be answered otherwise. Also, a system is not only limited to collect data, show charts, and send warnings, but it can also process the data in a smarter way, communicate with other systems and platforms, sending instructions or take action depending on the commands received. For example, here we list some examples. As it was mentioned before, a monitoring system does not focus only on structural parameters, but it focuses also on environmental and weather conditions for which the structural parameters are recorded. The example here is, for example, depending on the distance of visibility, fog conditions, the monitoring system can automatically switch on or off the lighting system on the bridge, or set the speed limit if the visibility is reduced, or can switch on the red semaphore at the abutment to close the access on the bridge in case of a special event. For example, after an earthquake, the system detects that the bridge moved or strains were too high and cracks happened. In these cases, the system can close the bridge immediately for the safety of the users and to give time to the authorities to reevaluate the integrity and the safety of the structure. Same for special analysis or studies that can be developed custom-made on specific requests. Some examples are fatigue analysis that we have already discussed, structural force calculation from strain gauge readings, like bending moments for which the bridge is designed, stray current, and dynamic identification that we present a bit more in detail now. This slide is about stray current. Stray current is an example of corrosion issue where a well-designed monitoring system can help to prevent corrosion of the structure. As you saw before with Daniel, there are corrosion sensors that can be used to monitor if any degradation of the materials happens, either concrete or steel. However, when corrosion is detected, it's kind of already too late, because when we monitor corrosion, it's because corrosion has already happened. Usually this is not too bad, because anyway, corrosion is a slow phenomenon. So it gives time to the engineer to take action, for example, to restore or apply corrosion protection. Anyway, in some cases, it is possible to prevent corrosion from happening. And how? Monitoring the cause of corrosion to keep the risks and probability of corrosion at low levels. By doing this, an action to protect the structures can be taken already when the severity of this cause increases, with no need to wait to see the corrosion happening. The example here is the stray current monitoring system, which in this case, I mean, it's the case of rail systems, so railway bridges. Rail systems typically use the running rails to return the current to the substation. However, as these are not perfectly isolated from Earth, a small fraction of the current can leak from the rails and then may cause corrosion. The figure shows stray current interference for a buried pipe, but still reinforcement in a bridge would be affected the same way. There can be accelerated corrosion where current discharges from the steel to the ground. So mainly when the current leaves the structure. On the right, we see a cross section with stray current sensors installed, highlighted in yellow. The first one is in the concrete slab in the transit corridor where the rail system is, so where the stray current comes from. The other one is installed at the base of the pier where the stray current is likely to leave the structures as the piers are obviously grounded via the foundations. In the chart in the bottom left, the structure to earth potential is plotted against time, days. The vertical blue line represents the midnight. And after this, we see a short period of few hours with a stable reading because there is no traffic, there is no rail traffic, so there is no stray current around. During the day, we see high peaks, negative peaks in the orange circle. Then this corresponds to the current entering the structure. Positive peaks in the red circle correspond to the current leaving the structure. So these are the more dangerous ones, the dangerous peaks. In general, these peaks show activity. So a change to either abnormally high or low values indicates that there could be an increase in stray current, so a higher risk of corrosion that could alert the users for them to take action to bring these measurements inside the typical working range, so they can protect the structure before corrosion starts. In this slide, we see another practical example of added values with the possibility to deduce information about the status of the structures based on some more advanced analysis of the dynamic response of the structures. On the left side, we see an example of structural accelerometers used for dynamic identification of the structures. Dynamic identification means to evaluate natural frequencies and modal shapes of the structures mainly, either to bending or torsional behaviors. And this calculation at the date zero can be used to confirm the design of the bridge and to confirm that the bridge behaves as expected. In addition to this, it can be used to evaluate the status of the structures on the long term. And how? As we know, these dynamic parameters depend on the masses and the stiffnesses distribution along the structures. In general, masses distribution is known because we know the geometry and we know the material used, but we don't know the stiffness because we don't know if there has been any degradation, for example. This is actually the goal of the analysis. A change in the frequencies or modal shapes could indicate a change in the structure or a change of certain material properties. Or, for example, the increasing of cracking, which also reduces the stiffness of the structures. On the right, we see an example of dynamic identification of cable stays. Here, modal shapes are well known and not very interesting. More interesting are the natural frequencies to which the axial force can be calculated from. Cable stays are cables, so elements with no bending stiffness, and their frequencies depend on the geometry, length, and weight, and to the axial force. So measuring the cable vibration, we can then evaluate the frequencies and calculate the axial forces with an accuracy of 5–10%. The picture of the guitar is just explanatory. The screws at the end are adjusted tight or loose in order to change the string stress, which directly changes the natural frequencies of the same. So by changing the stress, the frequency changes accordingly, and you can fine-tune the sound. Now we can go over to some conclusions. Conclusions here are briefly summarized in a few bullet points. First of all, a monitoring system brings added values to many areas of the bridge maintenance, operation, and assessment. It works with high fidelity 24/7 measurements. It offers significant advantages for quality control of bridge components like STU, joints, bearings when these sensors are integrated during production. And last point, this should be seen like one of the next steps in this field. One of the further developments will be probably to focus on data analysis and optimization to minimize the amount of data, but still to maximize the value of the information in there, avoiding, for example, to generate big amount of data, but still getting the best info out of it. Sometimes we see it from real cases. Data science will probably take importance in the monitoring field to optimize information, to extrapolate always better information, but also to help to plan the maintenance, to detect damages, or also to predict damages before the damage happens, so before it's too late. Anyway, we believe that a lot still has to come, especially because from the last years, the monitoring of structures has diffused really a lot also in the business, while more in the past it was more a topic for university or research. But now we see that it is gaining always growing importance, and it is being applied and requested in many real cases. If we think how technology developed also in other fields, things look promising also for the infrastructure, and we can just be impressed by the recent developments. Let's take the easy example of the car industry. Today there are sensors for everything: gasoline level in the tank, mileometer, failure of the engine. The sensitivity to this topic and the approach is changing a lot also regarding bridges. Sometimes the owners wonder like, but do I really need a monitoring system? Do you really need a sensor to tell you the level of the gasoline in the tank of your car? Maybe not, if you are willing to open it every 3-4 days or 300-400 miles to check and see. Same is for a bridge. The initial indecision is being definitely overcome because engineers definitely appreciate the advantages, the value of the information, and the worth of a monitoring system, like we explained a bit today. Thank you very much for your attention. Ryan, have we got any question?
Yes. Hi, Andrea. Thanks, Daniel and Andrea. That was a great presentation. We do have a few questions trickling in now. I'll just start as we are receiving them. First one is for pot bearing stresses, is a direct pressure tap or indirect steel hoop stress measurement used? I guess I'll give that one to Daniel.
Yeah, it's a direct pressure tap. Andrea can confirm, but that is what we depicted. Yep.
Yeah.
Okay. I'm just letting everyone see it. Send to all.
I mean,
okay.
Hypothetically, it could be done another way, right? Like we could get it the other way, but what we showed were direct pressure taps.
Okay. Next question is, thanks for the great presentation. How are these instruments, sensors, wiring, and cables, how can they be protected from the public or even wildlife, say?
It depends on the specific application. In general, there are conduits, cable trays to protect cables, splicing boxes to protect splicing, mechanical boxes to protect sensors when needed. Everything is IP rated. In general, not directly exposed to rain, sun, or the weather conditions. But yeah, depends on the specific circumstances in general.
Yeah.
Correct me if I'm wrong, Andrea, but I think a lot of those pictures were taken during installation, but then there's a box typically around a lot of those sensors, right?
Yeah, from the box you don't see much.
Yeah, exactly right. So in order to see the sensor, the pictures had to be of an exposed sensor, but the sensors were typically not exposed during function. Yeah.
Right, and then for the public, we sometimes put locks on the boxes that cover the sensor. There's access gates and things like that that keep people from accessing it.
Exactly.
Hope that answered that question. Next question is, how does an ultrasonic sensor work?
Ultrasonic sensor, it sends waves of compression and decompression of the air, basically. the ultrasonic technology. It measures a distance, the range typically from maybe 10, 15, 20 to 50, 60, 70 centimeters.
Right, same concept as like radar or sonar, right? Different waveforms or whatever, but the same concept. It's a bouncing signal that it interprets as distance, and they're really high frequency, right? Typically, extremely, I think.
Yeah, it should be.
Yeah.
Okay. Next question is regarding how to calibrate and establish a baseline for the sensors. Yes, so how do you establish the baseline for the sensors, strain gauges on steel members or bearings? And will the sensors be out of calibration as time goes on? And how do you calibrate them if they need to be recalibrated?
Let's say sensors are first calibration is done by the manufacturer when they do their proper test in their lab before they ship it, and they ship it with the calibration certificate. Then when are installed, it depends, because for the strain gauges, it depends also on the stage construction in which they are installed. Because if it's installed in an early stage of the building construction, you follow all the story of the strain at that point. But if it's installed at the end of the construction, you lost all the permanent loads applied to that structural element. So it's something that has to be designed based on the specific project, specific needs, and so on. For example, for what we saw about the fatigue analysis, we are only interested in the cycles generated from the traffic load. So we zero all the readings, we bring them to the average to zero, because we only want to see the changes, the waves. In general, if the permanent loads are important, then it has to be planned carefully also with the bridge designer to follow the stage constructions and to know which stresses are taken into consideration and which stresses are lost.
Yeah, for example, if half of the bridge is built and we start putting our sensors in at that time, we'd have to work with the bridge designer to ensure, okay, at the time of the sensor placement, this is what was currently constructed and what theoretical loads are being applied at that time, dead load. Okay, and then let's see what the last question we have. I see. Do you have recommendations for monitoring protocols in function of the expected type of damage in bridges?
I would say there is no a standard protocol. The damage depends on which element you are looking at. Depends on how do you define the damage. Let's say a crack of 1 millimeter, is that a damage or not? A crack of 0.5 millimeters, is that a damage or not? A change in the frequency, is that a damage or not? It depends a bit of many factors. So I think there is no standard protocol that can be applied. It depends on the specific case. It depends on the specific case.
Yeah, you would general, do that with min-max values or something.
It needs a lot of knowledge and expertise for that specific situation. So someone that knows that structure very well, or someone that knows that structural element very well, or someone that knows that component very well.
Right. Probably designed on the back end. And there's not a specific plan because it depends completely on the particular component that may fail, right? So.
Okay. We have time for one more question. Let's see. Is it correct that strain gauge monitoring can only assess transient loads, but cannot assess permanent dead load stresses or forces?
No. They can measure everything. It depends on the time when they are installed. Because if I install the strain gauge at the end of the construction, when the bridge is it's open, for example, I install the strain gauge there. The strain gauge doesn't track anything that happened before, because simply because the strain gauge was not there. Simply because the strain gauge was still in the carton box, maybe in the office. So it doesn't keep track of what happened before it was installed. But if also permanent loads are to be measured and so on, the strain gauge has to be installed on a very early stage of the construction. For example, sometimes Easier application, an easier example is when a strain gauge is installed on the rebars, steel rebars, because that installation usually is done when there is not yet concrete, right? So if there is no concrete, there is not stress and strains on the rebars. So that's the starting point. That's fine in that case. But in other cases, if it's a steel beam, it has to be installed on a very early stage of before the beam is in place, for example. So before the beam is subjected to the dead load of the beam itself.
Okay, excellent. So that's all the time we have for questions. But we definitely want to see you again, and we will have additional PDH courses coming out. For example, we will be having a bearings PDH course coming out in April, and in June, we'll have an expansion joint course, and then in August, we plan on having a flexible plug joint course. So we definitely invite you to attend those, and they'll all be registered as well with the Practicing Institute of Engineering. Also, we'd love to see you on our LinkedIn page, and you can see updates on current projects we have around the world, as well as stay in contact with us. So please write us a message or stop by and take a look, like a page, like a post, and it definitely helps us, and we appreciate it. And then in the next few days, you'll be receiving your course certificates. And please note, if we didn't address your questions at the end of the slide, we will email our responses to you. That way you get a closure on our course here. So thank you for your attention, and please don't forget to visit our website, magebagroup.com, to stay up with current events. And we hope to see you at our next webinar. Stay safe. Thanks.